All right, we're going to look at sigma notation now for finding area. So we said before that if we're adding up a bunch of rectangles, another way we can do this is with sigma notation. Sigma notation is a way of adding a bunch of things together, which we're doing when we add all those rectangles. So how it works again is this lower notation tells us where we are starting. The upper number tells us where we're ending. And then this gives us what the thing that we're filling in each time. So here, our change in x would still be, that's kind of like the width of these rectangles. And then our function height right here would be the height of the rectangle. So if we plug in the different numbers in for here, that would give us a repeated thing over and over and over and give us the full one. Because the first number we're plugging in would be 1. Then we're plugging in the second height all the way to the last height. And then what we're going to look at later is if we do the limit as the number of rectangles go to infinity, then it would give us the exact area. So how do we find out that change in x and the x of I there? Our change of x formula is the same thing we've seen before, b minus a over n. Our x of I here, the x that we're plugging in for that would be our starting amount, which is a. Okay, that's the same a we see here, wherever we're starting, plus the change in x, and then we increase that each time by I. So whatever I number you're putting in, that would be the amount you're going over. So on the first one, it would be your starting point plus that change in x once. That would give us your first rectangle. If you want that next rectangle, now if you plug in the next number up, which would be 2, you would move your starting point a plus the change in x over twice. Yeah, now that's going to give you the next one there. If you go up the next number, which sigma notation does, now you'd start at a, move that change over once, twice, 3 times. That would give you the next point there. So you just keep moving over the change in x more and more each time. So those are the 2 little equations that you're going to need when doing this. So let's try one out. They want us here to find the area of this, same that e to the negative x one we've seen before. See if we can come up with an expression, but they say do not evaluate. So let's find out those things. Let's first find out our change in x here. And we've previously seen this one. So this would be our a and b values, which here is a is 0, b is 2. So we got 2 minus 0. Except here we're just going to generalize and not put anything in specific in. It's just going to be over n, which this then ends up just being 2 over n. So that's our change in x value. Next, we're going to find what's our x of I here. So that's our a value plus our I times our change in x. So that ends up being here. Our a value is still 0 plus I, and then our change in x that we just got is 2 over n. And so 0 plus something isn't going to change it, so I'm just going to change this to 2i over n. I just multiplied this times this, because this we could think of as over 1. All right, so that's our x of I. Okay, and then the last thing we're going to find out is what is f times x of I times our change in x here. So that's what we see there. So let's plug in what we got now. So our function f is going to be in this problem e to the negative x. So this is going to be e to our negative x of I, because that's what we see here, times our change in x. So what does that end up being here? It would be e, our change, or our x of I is right here. It's 2i over n So this is going to become negative, plug it in, 2I over n. And then our change in x is what we had before, times 2 over n. So if we want to write this out now as an area, as a limit, as the number of rectangles go to infinity, now we just want to fill in all our stuff into this area equation here as the limit, as the number of rectangles here goes to infinity. So if we write this out, the area would equal the limit as the number of rectangles goes to infinity of our sigma notation. We got n here, we got I equals 1 here. And now we want to fill in. So what we're filling in is this. We just found that right here. We're just going to copy that over. E to the negative 2I over n times 2 over n. So that would be our equation here to find that. So another way you could write that too, since this is not including I, you could also think of this as a limit as n goes to infinity of 2 over n times this over e to the negative 2I. So either way of writing this would be okay. That answer is good. This answer would also be acceptable. So either one of those, you could see it written either way. All right, let's try another one. So the next one, what is this one going to be? So again, let's find those same two things, or a couple things here. Change in x first is our b minus a over n. Here it looks like our a is 2 and our b is 6. So let's find those first. All right, so if we plug that in, we got 6 minus 2 over n, which we can simplify to 4 over n. So that's our change in x. All right, next let's find our x of I. So that's our starting value plus I times the number of change in x's. So here we're going to end up with starting value on this one's 2.0 plus I, and our change in x here is 4 over n. I'm going to simplify that by just combining our 4 and our I here. So it'd be 4I over n. So there's our x of I. So now let's come up with our f of x of I times change in x. And the reason I want that, that's what we're putting after our sigma notation. So that in this problem is going to be our function is 7 minus x. So we're going to have 7 minus x of I, because this is what we're plugging in. That's what we see here. So that's what we got to plug in here. Times our change in x. So here, if we plug in what our x of I is, that was what we had in the just previously here, right here. So 2 plus 4I over n. And our change in x here is 4 over n. So simplifying that, make sure we distribute here. We got that negative sign. We need to distribute. And so we're going to end up with 7 minus 2 minus 4I over n times 4 over n. And we can simplify that a little bit further. That's going to be 5 minus 4I over n times 4 over n. All right, so what is our limit written as now? Our area is going to be the limit as n goes to infinity of our sigma from 1 to n, first rectangle to n, of all that stuff we just came up with now. So 5 minus 4I over n times 4 over n. That answer would be correct. You could also, if you wanted, take that 4 over n and put it in front of the sigma notation, since that can be done after you've done all these other things. So that would work too. So this would also work as a answer here. So either one of these two would be it. All right. One more here. Let's have you guys pause the video and try this last one out here and see if you can come up with this final one. So see what you get here. All right, let's see what you got. So first one here, if we're doing this one, here's our A and our B here. So subtract those over n. We end up with this. I did simplify by dividing is the same as multiplying by reciprocal. So I did that to both top and bottom. That would cancel, and we would end up with that. Now our x of I is our starting point plus I times our change in x. If you fill that in, you should get this. Lastly, our function now times our change in x. Our function here is sine x, and if we're finding that at x of I, it would be sine of x of I times our change in x. We know our change of x from before, and this would end up being sine of this if we plug this in for x of I, which it's equal to. Here, one thing to be careful, do not multiply these two things together, because this is sine of this times that other stuff. So don't times those together. All right, last thing then, you'd want to write this out then as our area. So our area would be the limit as n goes to infinity of our sigma from 1 to n of the stuff we just found out here, sine of I pi over 2n times this. And again, you could also write that another acceptable way would be to write it as pi over 2n times our sigma here of sine of I pi over 2n. So that's either one of those would be acceptable here. Now, one thing I do want to bring back, looking at this stuff, you could use this to do our, or find that same thing we did before. So if you're looking at, so the sigma stuff is another way you could do this in the calculator. Remember doing this problem before where we had the -2 and we had entered all those individually. You can use your calculator to do this as a faster way. Remember typing all those in and it was kind of long and tedious. You can use sigma notation. So the one we had done on the last example was this with the number of rectangles equaling 10. So if we were to fill in 10 in for the ends, we should be able to put this in our calculator and use it to do it. So how you do sigma notation on the calculator or summation, hit your math button, and then if you go to the bottom, and I'm going to get there quicker by hitting the up arrow, we can type this in. So I'm going to hit up arrow here. We're looking at the summation one, this one right here. So hit enter on that. We want to pick a variable for this. I'm just going to use x. Over here we had used I, but it doesn't matter. We'd want to start it at 1. We want to end it, so you got to hit the up arrow. We want to end it at 10. So we're going to type in 10 for 10. We're going to use 10 rectangles. Hit over to enter your function, and now we want to enter this. So we want to do e to the -2, and then we got to get our variable in there, x over 10 here, and then that's going to sum up all the heights. So that's all the heights summed up. Now we got to multiply by 2/10. So if we take this times 2 over 10, that should give us the same amount we did before, 0.71881. If you go back up here, that's the same value we got when we had added all these together. You can see it right here, same value. So you can use summation to also add these up if you got a bigger one like the one we just did.